or call them out to you. Product rule, quotient rule, function of a function rule, or whatever you'd like to call that third one, your own name, all right? So there's those that are about to pop up. You're also about to get some area. You could get some volume questions because all of this comes under calculus. Now when you need an area, this is a little bit of revision because you're going to be sitting your mid-semester. There are areas in that mid-semester, there are volumes in that mid-semester, but they're of basic functions, okay? Basic functions. But we're going to do a bit of a recap on some things if we have time to pass through. Some areas, but now you're looking at trig functions. So you better know how to draw the trig function, because if you don't know how to draw the trig function, then you don't know how to find the values, okay? The x values or the y values you're going to need. So that's the fun that's about to appear. However, you're about to see me skim through some of this, because when we had this last year, we used to run the 1.5-hour exam in the lecture, and then we would do a short lecture of half an hour. So what happens is Dave had all these slides in here that he's kept, but really they were just to make that pad out the one from last year. So there's a lot of interesting facts in here. They're really lovely, and if you want to sort of slow it down, play the recording and just slow it down frame by frame, all right, because what I'm about to do is just skim past all of that. I'll sort of give you the verbal, but none of this initial part gets examined. So here's what we've got on page 100. It starts on your page. It says straight away, the derivative of a sine of a function. So before I get to that, he's got a lot of slides here, and this was because he was just investigating it. So it was a nice little patter for him because he said, well, I'll just fill in some time and show them. You remember that the derivative is always the gradient of the tangent. So what he's about to do is investigating the tangent. That's what the blue line is. And when he investigated the tangent and plotted those dots, he actually got the graph. Now that green graph is a cos graph. So what it's actually said is that the derivative of a sine is going to give you the cos. That's what that's saying there in words, okay? So then I'll go, there's the cos. All he was doing was finding the gradient of the tangent. He was plotting it as he went along. And when he plotted it, he realized that it wasn't actually the sine curve, but it was related to the sine curve. So it turns out to be minus the sine curve. So the dotted one was the sine curve, and then it got flipped over. So again, it's just a matter of interest. It's nice to collect it. This one goes for a little while, so I'm going to really speed through it. Again, all he's doing is he's investigating the gradient of the tangent. As you can see, he can see that the gradient of the tangent is doing this. He's plotting it. And it turns out that it's always positive. So one thing you know about your graph is that it's always above the x-axis. And this one is the one that says the derivative of tan is sec squared. Now again, I'm going to zoom through this because he's just relating it to the sec curve and then he's squaring it. So that's all he's doing there. There's the sec curve, and then he squares it and he gets the darker green. Okay? So, again, I'm not going to do that either because this was just a nice little proof, because it says show that the derivative of tan can be found another way to end up at sec squared. That would mean you would do the tan. I won't do it, but I'll just say that the tan is always defined as sine on cos, and then you'd use a quotient rule, all right? And it's just saying use trig identities and the quotient rule to find that the derivative is sec squared. So we're not going to dive into that. That's where we're diving into, which is at the top of your page 100. Now here's the thing you're going to do. If you've got a highlighter, all right, what you really need to pay attention to is it says that the derivative, and the way it's written, some people don't like it, it's something you might not have seen before. D dx is actually asking you for the derivative of what's about to follow. Now it doesn't have to have the brackets around it. You might like the brackets around it. But what I want you to highlight is this guy here, the f of x. Because what you're going to see is the sine of. Now you're going to be very happy if it says the sine of x. But what if it says the sine of x squared? What if it says the sine of 4x plus 2? So can you see that the function is going to change? So the first guy, sine of x, that I wrote, is the simplest of all of them. But don't expect just simple things. So as you go along, highlight what actually sits next to the word sine, because that is now your function. The function here is x, the function here is x squared, and the function here is 4x plus 2. Now why is it vital that you highlight it? Because it says the derivative will be, first of all, it's the cos of exactly the same function. So it doesn't change. It doesn't go down, doesn't go up. It just stays exactly as the function. But what you put at the front of it, it says is f dash of x. So it's about finding what your f of x was and then saying it will sit there with the word cos, but I will do its derivative and put it at the front. So that's what an f dash of x stands for. Same for cos. Again, this is asking you for the derivative of. You'll notice I'm going to highlight this guy here, and then it says it will be minus, so the sign changes. You've got the sign of the function, but what do you have at the front? The derivative of the function. So again, this could have been the cos of x as its simplest, the cos of x squared, the cos of a 4x plus 2. So that's how you're building them up and how they're going to try to make your life harder. And the same with the bottom one. Highlight this function here, and again, it's a sec squared, so it's quite different to the others. It's a sec squared, and again, you're going to be looking for the function, and then you're going to multiply by its derivative. Now, you've got a whole page of examples to go. So here we go. So up on top, the main thing is, when you write this in on your resource sheet, you can see that sine goes to cos. That's the main guy. So the derivative of this will be a cos of x. And what I'm going to do is out the front, I'm going to put an arrow because I want you to say, have I checked its derivative? The derivative of x is just a plain old 1. So I really didn't need it, but I've put it there just as a good check. Round 2. All right, it's got the derivative of cos. So the words say that this will go, the rule says it will go to minus and it will stay as sine of x. And again, I'm going to put a number there. So what's the derivative of x? And the answer is a 1. Now again, I didn't need it. It just says minus 1 times sine of x. And again, the simplest for the tan, again, the formula says, or the notes say that for tan, it will be a sec squared of x, and always keep an eye on that derivative of the function. And again, it's a plain old 1, so it hasn't done much. Now, they're the three most basic. So you might want to write them down on your resource sheet when it comes time for the quiz. They're the most basic, but have a look at the rest. Now, the rest I've highlighted in my book that things change. There's a 5x, an x on 3, a 2x, a sine x minus a cos x. So things get complicated. So I want you to use your highlighter, if you've got one, and highlight this 5x. That's my function. So first of all, sine goes to cos. So I will put the word cos of 5x. And then I've got this put out the front. The derivative of 5x is a 5. Now, whether you put it there to start with, that's fine as well. I'm just saying, make sure you've done it before you walk away from it. I'm not sure if he put it. Are we all finished with that one? We're all good? So the next one, next page, again in your book, I've highlighted. And the reason why we ask this question a lot is because a lot of people don't understand that this is 1/3 of x. Now, it's just like a 5x. It's just like a 1x. All right? It's just a constant. So when I go to do this, I know that it will be minus because it's the word cos. I know it'll say sine. And the function itself doesn't change. And then I'm supposed to multiply by its derivative of the function, which I can see is a 1/3. And that's what you want to do, just little steps like that. Now, the next one comes up, and there's a constant 3. Now, the constant at the front just sits and waits. So that means it's 3 lots of, and then I work on the derivative. So the derivative of a tan is a sec squared of 2x. And again, I've left that gap. What's the derivative of the function? Derivative of 2x is a 2. So together it's a 6 sec squared of 2x. So remember, the angle, okay, the part where the angle sits doesn't change. All right? So the next one says, now it's come to us with a little bit more. So it says, I'd like you to find the derivative of sine of x minus cos of x. So this is just like saying when we used to have simple functions that had first guy and then it would have had a second guy. And they just say, what's the derivative of? And you have to do the derivative of the first guy and then move on to the next guy. It's the same sort of thing. So first of all, the derivative of sine, it was called out as cos of x. I've done my check. It's only a 1, so I don't really need to put it there. Then it says minus, and now I'm doing the derivative of a cos. Now the derivative of a cos is minus sine of x, and I've done my check. That's what that little arrow tells me. Can we tidy it up? So it says cos of x, and it says plus sine of x. So the derivative of sine x minus cos x is actually cos x minus, plus sine x. The next one comes up. We've got a few things to deal with. This guy here is a constant, so I'll put the 4. Within the function, see this guy here, this is the function. There is only one guy with an x on it, the other guy is just a constant. So a pi on 2 is just a constant. Now I'll keep that in mind because the word cos goes to minus sine, so I'll put here times by minus, I'll put the sine of a pi on 2 minus x. And what's the derivative of what I see in the function? Minus 1. So I've got that there as well. In total, it's 4 times a positive 1. So it's 4 times sine of a pi on 2 minus an x. So I would write all those things. I would write the minus and then the next minus because they're the things that we know we want to trip people on. And the pi on 2 is another thing we throw in because people think they can do a derivative to it. But there's no x involved, so it's just a constant. Because the word cos has to go to minus, all right, and then it already had a minus. So this guy was already there. Oh, sorry, why is that there? No, this guy was because it was the cos going to sine, okay, and then this one was because it was the derivative of f of x. Yep. So here's the next one. It's gone to tan of, and it's got a bx. So again, that can throw people, but the word tan always goes to sec squared of bx. What's the derivative of the function? So it's algebraic, so it's just a b. All right, so it's a b in front of sec squared of bx. Now, the next 3, I've put on my little reminder, rule, rule, rule. So I've given you a clue. I need a rule for this guy, the rule for the next one, and another rule. What do you think? What rule do you suggest we need here? What rule do you suggest? This is the problem. The problem is you can't see that that needs a rule. And if you can't see that that needs a rule, then there's going to be a big hiccup here. That's a product. So what I want you to do is I'll write it again and I'll say this is x being multiplied by the sine of x. This is going to need a product rule. So when it comes time, and I know it seems a long way away, but this is B2, and the quiz for B2 doesn't happen till after the break, second week. You want to put the product rule, the quotient rule, and anything else you think you might need on your resource sheet. So put a little highlighter section here and say to yourself, remember to put this into my resource sheet, onto my resource sheet. Now I quote my product rule as VU dash plus UV dash. Now if this starts to get a little bit too much, then the backup is just set things out, put your U and then your U dash, put your V and then your V dash, all on the side. So it's like cooking, prepare it all, do the prep, okay, do the prep, and then say the derivative of x is 1, the derivative of sine is cos. Now everything's ready on the side, so I'm going to say the product rule said V, so I'll put sine of x, and I tend to do dots for multiplication if you haven't seen that before, so as not to confuse ourselves. So that's a V with a U dash being multiplied, plus a U with a V dash. So I'll tidy it up. It's come out to be sine of x plus x times cos of x. And what do most people do? They don't see, all right, the freight train coming. It's called the product rule, and they just get hit completely. So it's about citing it. What do you reckon the next one is? It doesn't look like a product rule. Any thoughts for anyone that's already got their eyes on it? Not a product rule, but how would you call it? Not a product, not a quotient. How do you call the third one? So it was either called a function of a function, or some people from school called it a chain rule or a composite rule. So whichever one you called it. So what you're staring at there is really saying, all right, it's like me having a function. This is what I'll write on the side. It's like me having a function that said something like this. All right, so it's got a bracket to the power of 4. And when we got this back in the first semester, that chain rule or function of a function rule said f dash was going to be, we dropped the 4, the bracket stayed the same, we dropped the power, and we multiplied by the derivative of what was inside. Now you can do it slowly with a substitution, but then we said there was shortcuts to it. So then this would have turned out to be 8x with a bracket, x squared plus 3 to the power of 3. Now that's the sort of thing, it's about dropping, continuing on, and then remembering to multiply by the derivative of what's back inside. So see the way this has been written? This, in other words, is asking you for the derivative of sine of x being squared. Now we don't write it that way because it takes more time to write it. So we actually are allowed to put the 2 where it was. We are allowed to do that. But I've written it this way so you can sort of see it the same as the function over there on the right-hand side. So here we go. It says you want to do the derivative. The 2 drops. Then it says sine of x, and I drop that number down. And then I multiply by the derivative of what's back inside. So it's going to be a cos x. So in fact, it turns out to be 2 sine x cos x. Now I didn't have to rewrite it with the brackets with the squared on the outside. It's assumed that you know what it means. But even if you just jot it down and say, well, I might need that little extra line just to help me out. Now the same's about to happen on the next one as well. So it says, find the derivative of, and again, I'll rewrite it just so you might say, I need this, because remember, it's going to be a lot of weeks before you actually get quizzed on it. Now it's got the 3x inside there, and it's being squared. That's actually the question. It wants the cos of 3x that was being squared. So this one obviously has a few little hiccups. It's going to be a slow one. I'll go. 2 drops down the front, cos of 3x, and all of this was then dropping to the power of 1. I then needed to say what's the derivative of what I'm looking at inside. Now look at what's inside. Get your highlighter if you need it. What's inside is the cos of 3x. So the derivative of cos is minus sine of 3x. However, I put another little arrow because it's also got a derivative of the function in there. Now I don't try and do that fast. I slow right down. And I'll explain it again. The 2 drops down like in a function of a function. You write the cos of 3x and the power drops by 1. I'm multiplying by the derivative of what's inside. It's minus the sine of 3x, but that 3 is causing me again to have another 3 out the outside. Put it all together. Looks like it's minus. It looks like it's 6. It looks like it's the cos of 3x followed by the sine. And it doesn't really matter which one was written first, because it's all being multiplied anyway. It's all being multiplied anyway. So tread slowly through that type, rewrite it if you need it, but all it is, you might want to say to yourself, those bottom 2, they're the function of a functions. And on the very bottom it says to you, what about if that you were being asked to differentiate the sine of x squared? Now that's asking you a different question. Here is the function. All right, so here's what I'm about to do then. All right, y dash should equal. The derivative of a sine is a cos, so I'll put cos of x squared, and then I'll put multiplied by the, get rid of that, I'll get rid of that for a second, come back here, and say multiplied by the derivative of what's inside. What is the derivative of what you see inside, the function? It's a 2x, so that sits in the front. So in fact, I'll just tidy it up and write it again. This is going to be the answer, which is different to the one we did before. So it's important you notice where the square is. Is it the whole word sine of, or is it just the angle part that was being squared? Righto, they're derivatives. Now, just as a bit of an aside, we don't get any questions in our lecture. There's some spares that Dave throws in because he always thinks we might get time. And if I get time, I will come back to it. But as soon as you find the derivative of any function, you really should be prepared to find the equation of normals, the equation of tangents, all that sort of stuff can be asked even in this spot. You can also be asked to find stationary points, because that's also needing y dash. So all the things you used to use y dash for, come back, all right? But we don't put much in here, so I was just having a look in the tutorial. Now this guy here, again, I'm going to flip through because he was padding out the lecture last year. So he's just sort of going through and he's noticing the sign changes for the first and the second. He's looking at their concavity, so don't worry, you don't get examined on it. This is now the reverse, so now you're on page 101. So, again, if you know what the derivative of a sine is, the whole idea of an integration, okay, a primitive, is that you go backwards. So this is what it's going to say. If we knew that the derivative of sine was cos, then we know that the integral of cos dx is equal to sine. Now there should be a good old plus c. Now I'm going to put that there because you're going to get examined on Thursday or Friday, and you want to make sure that if it doesn't have any limits on it, it's called an indefinite, then you really should put those plus c's in. So I better start brainwashing you today. So the derivative of cos was minus sine. Now the first thing you notice is it says that means that the integral of this goes back to giving you this. But you'll notice that that's not how most of us remember it. What we tend to do is we tend to say, oh, you mean that the integral of sine x, and we throw the minus on the other side. Now you've got it written anyway. Yours is waiting for you. But I've put it on that slide there, although you don't have a space for it there. And this one just says the same thing. If you know the derivative of tan is sec squared, that means you can go backwards. Now these should have plus c's on them, just so you can start being perfect for Thursday and Friday. This says, that's great, because what I just put in front of you is all the basics. So see this guy? This is the basic guy there, there's the basic guy. Now that'd be great, but we know they don't just give us basic ones. So the only ones that we can actually work with, and it's about to lead to this, it's saying here, we've already done this. The derivative of sine of f of x would have been the cos of f of x multiplied by its derivative. Now, if we were going to do the same thing I did on the last slide, we were going to get this. So the integral of the right-hand side should give you the left-hand side. But these get a bit complicated, okay? So the idea is we don't actually, we're not always equipped. We don't have enough time as well to cover everything. So you might have been in extension perhaps in your lifetime when you did extension maths at school, and you would have been you would have been dealt some of those. But what happens is the only ones we deal with, and it's on the top of your page 101, the only ones we deal with are, and how would you describe these? How would you describe them? See how it says sine of ax plus b? So now I'm saying I'm only going to concentrate on that type of function, because when I do my integral, that type of function, and I'll put my sort of pen on there, that type of function has a constant about it, and that's why the constant lives here. Can you describe an ax plus b in any way with all your expertise? What kind? Yes, it's linear. So the only type, and if you highlight up on top of page 101, the only type of functions that we will throw at you will be cos of a linear, sine of a linear, sec squared of a linear. That's when you're integrating. So have a look at all the 6 examples that are waiting for us. Have a look and highlight and say, you know what, they're just straight lines, because the x just gives me a linear, x, 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 there's a 5x, there's an x on 3, and then there's a 7 minus 3x, still just a linear. So the only ones I can integrate are linear. And the trick is, see there's an a value, so I'll just go to the table that you've got in front of you. The table that you've got in front of you says exactly that. I can only integrate something that's linear, and what I'll keep an eye on is the a value. Now the a value is just, you could call it the gradient of that line, because that's really what it was, if you want to link it to that. Because when it comes over here, I need to put a 1 over a in front of it. So again, this is linear, and keep an eye on the a value because it's got to sit there. And then keep an eye, this is linear, keep an eye on that a value because it has to live under here. So are you ready and equipped? Have you highlighted top of page 101? All right, we're leaving that for a moment. It's just a bit of a discussion. He's going through there. And then these are the 6 that we want. So here's the first one, sine of x, it says. Now, I want you just to say to yourself, it's linear, yeah, because it's got a plain old x. And what's the a value on this one? 1. So when I go to write it, you'll have your resource sheet with you. The integral of sine, this is the one that goes to the minus cos of x. Now the 1 on A, do I really need it? Well, I'll put it in, but I'll just say that that turns out to be minus cos of x with a plus c at the end of it. But I'd always check it, because it's the time that you don't check it that you're going to get stung probably. The next one's got the cos of x. Again, I just want you to say, is what's in here linear? It should be. What's the a value? So I'll say a is equal to 1. The integral of cos is just a sine of x, and it says it should have had a 1 on 1, so I'll put it in there, but you know that it's turned into a 1 anyway, so it's gone. And again, the most basic one, sec squared of x, is this linear? Check what the a value is. And again, sec squared goes back to a tan of x, and I'm checking it's a 1 on 1, so it really isn't needed. I'll put tan of x plus c. So they're the three basic ones. Not going to hurt. Any of those are not going to hurt because the a value was 1 in all of them. So here we go. First one that has a 5x. Now your brain has been on derivative mode. You need to get it out of derivative mode, all right, because you are integrating. You'll have your resource sheet next to you. The integral of a sine, it says it goes to minus, and it goes to the cos of 5x. Now you notice I write that down first, because then I come back and fill this in. What was the a value in this case? A 5, so there should be a 1 on 5, a minus 1 on 5, like that. Now I know what often happens. A 5 appears but in the wrong spot. It has to be in the denominator. Again, the next one we ask, because we know that you're all lovers of fractions. This is still linear. What's the a value in this case? A third. So when I go to do it, first of all, the cos gets converted over to a sine. So I write the sine of x on 3. And then what's supposed to be out the front is a 1 on, and I'm actually going to write my a value, so I will show you what it is. Because again, because you're all lovers of fraction, what's a 1 divided by a third? 3 sine of x on 3 plus a c. So I show every little step, because even that 1 divided by a third gets people. And there is one more. So again, if you set yourself up and ask, it's linear. What's the a value? In this case it is a minus 3. So sec squared goes back to tan, so I'll write the tan of 7 minus 3x. I will then put my 1 on, and I put my minus 3, and I've got my plus c. Now there's not a great deal you can do to that. In an exam, not that this is in your next mid-semester this week, but when you're in an exam, you don't need to waste any more time on that. There's really nothing else you can do. So it's correct as it is, all right? Because you guys are trying to find time to save. So you're just going to get yourselves into a good mode. Now the application, like I said before, once you've thrown derivatives at you and integration at you and primitives, then we can ask you lots more things. So areas and volumes are coming back, all right? Now, see this first question? It's not too bad because they've quoted to me the 2x values. However, what you should always do, this is a bit of revision for your test coming up this week, is you should always be able to cite your diagram, because if you don't cite it, you don't know if there's some of it above and some of it below the x-axis. And how does that make a difference to us? Makes a difference because something that's under, all right, needs to be sorted out, because the ones that are under should have absolute values around it. What happens if you just go, and I'll put it down, but I'm not going to continue. What happens if you just go wildly, you know, say like this, from pi on 4 to pi on 2 without citing it? What can happen is if there is a bit above and there's a bit below, all right, a bit above and a bit below, then they merge, and that bit that's positive goes with this bit that's negative, and you'll get a smaller area than you should have got, okay? So that's the danger of it. So don't go straight into that. Instead, do me a sketch. Another bit of revision. It's not for this week, all right, because you know you're not going to be forced to draw trig this week, but can you remind me, you did it last week, what a cos curve looks like? Talk to me about its amplitude, talk to me about its period. All right, what do you reckon? Call it out, guys, when you're ready. What can you tell me about a cos curve? Where does it start? At 0 or high? Up the top. So I'll go like that. Now I'm even going to do this. I'll just go through one cycle. Now I'll ask you for the period. So this is a bit of revision. What's the period? Well, I go back here. The period will equal 2 pi divided by 2, which tells me that the period is pi. Now, I've drawn one whole cycle, so now I can say that it must have ended up high at the pi, which means it must have got its low at the pi on 2, which means half of that again. This was happening at the pi on 4. Now, without much effort, all right, except the basics from last week, I can now see that the area I was looking for, and it says from bounded by the curve, the x-axis, and these two lines, turns out that it is all under. Now, it's all under, okay, so it can be taken completely together, but I'm about to bring in the absolute values. Now, I told my groups, and I sort of make sure everyone hears it over and over, that absolute values are great, but it doesn't mean you go wild on them, because sometimes an area should not have absolute values around it. If you know your area is above, it never should have come out to be negative, and that's a sign that you've made a mistake in your calculations. So, I've got the absolute value, because it's needed, because it's under, from pi on 4 to pi on 2. The curve I'm talking about is the cos of 2x, and it's with respect to x. That's what the dx means. Now, we have just figured out the integration, the primitives. So here we go. You've got it on top of page 101. It says, and this is my square brackets, it says the 3 stays there. It can come out, it's a constant, but I'm just going to leave it there for the moment. The integral of cos turns out to be sine, so I'm going to put the sine of 2x, and it's needing a 1 on. What number do I need to put it on? A 1 on 2. And then it says from pi on 4 to pi on 2. Now, I've got absolute values around the whole thing. Now, you might have a bit more space than me, but this is going to take us a little while. So it says absolute value. Now, I'm always going to try and be economical. So this is a 3 on 2 multiplied by the sine of 2 times pi on 2. I'll come back and talk about it, but I've written it down. Then it says minus, and then I start again, 3 on 2 times the sine, and I'll put 2 times pi on 4, and then I'll put my absolute values. Now, I've shown all that substitution. Now, on my resource sheet, which I don't have right now in front of me, but it's in my head, I know some trig answers. If you don't, you better get your calculator out. Be cautious, though, because sometimes they're exact values. Remember all those guys with square roots? 45s and, 60s and 30s. If we have any of them in our lives today, then you want to make sure that you put those guys on your resource sheet. So here is what I'm looking at. Now, I'm going to make my life simpler because I go, this is 3 on 2 times the sine of pi, which I know is 180, minus 3 on 2 times the sine, and this guy is called pi on 2, which I know is 90. Now, there's no problem if I go to my calculator. Now, I'm in degrees. Degrees is faster to type in, but as long as you're happy about that, otherwise be in radians, all right, but I'm much happier in degrees because I know that says the sine of 180, and then I go across and say, just keep multiplying all that out times the sine, and I know that's a 90. Now, I get an answer. Anyone else get an answer? I'll wait. It's a negative, and I'm expecting a negative answer. So it doesn't throw me that I know it's negative. That's why the absolute values are waiting for it. Any ideas? Okay, so it came out as, and what answer was it? 3 on 2? 1.5. So I'll tell you, anyone who does the first bit, that's fine. Or as Alex said, if you put the absolute values, because calculators, the newer versions, have them anyway, so I'll put that this answer is a 1.5, and it was an area, so I'll put units squared. Now, we've got our answer. Now, I tried to be efficient, which means when I pushed it in, I didn't go into radians. You're most welcome to, but every time you go into radians, you've got to push pi on 2, pi on 3, pi on 4, and things like that. So you're most welcome to do it, but it's a little bit of a time saver. You're also going to have your resource sheets anyway, filled with all these facts. Are we ready for the area bounded by? Are we ready for that one? If you're ready, you need to draw it, because what you'll see is, it says 0 to pi, the next one, so I'm just getting ready once I see all the i's have finished. Find the area bounded by this curve, the x-axis, and, again, there's a problem if you go straight to this. Now, you don't want to waste your time, because the people that do that are going to hit a big brick wall and then go, oh, I should have started it this way, and you've wasted a lot of time. So don't ever go straight for the obvious. Don't go for the obvious. You need to see it. So here we go again from last week. What does a sine curve look like? Where does it start? Starts at 0. Now I'm going to go through one cycle and then I'll ask you some more. It looks like the amplitude is 1, so a bit of revision, it's there and there. What's the period? Well, I'll go and investigate. It looks like the period will be 2 pi divided by 4, which is a pi on 2. Now because it's a pi on 2, I'm going to come back and put a pi on 2 here and a pi on 4, because it's very symmetrical. So if you know where it finished, then the halfway was at pi on 4. But I was asked to go from 0 to pi. So what does that mean about my diagram? Put another one in. So go put another whole cycle in. Now it's up to pi. This is that guy there, all right, will be a 3/4, 3 pi on 4. It said, now first of all the diagram's ready, and it said, find the area bounded by the curve, the x-axis, and these lines. So you mean you want that, and that, and that, and that. Now, if you had done, you know the other one where everybody takes off and goes straight for 0 to pi, anyone want to take a guess at what their answer would have been? Because now you can actually see what their answer was going to be. Would have been 0. So all those people would have done heaps and heaps of work. They get 0 and then they go, I've wasted all that time. And that's why you don't want to do it. So now we can see it. Is there a shortcut? Because there is a shortcut. Anyone want to suggest? I don't want to do 4 areas, so how many? 4 times. You could have done 2 times. It would have meant 2 of these and 2 of these, or 2 of these and 2 of these, but they're really just the same because it's symmetrical. So it's actually going to be, so I'll put here, the area will be 4 times, and I'm just going to take the obvious, the first guy, because he's positive. So I want 4 times the area under this curve, so I'll put from 0 to pi on 4, and then I'll put the word sine of 4x dx. Now I'm just going to pause and say, can you see why it's 4? Without the graph, you won't see the 4, and without the graph and your graphing skills, you won't see the pi on 4. So it's up to you to be good at your graphing skills from last week. Now I think we're ready to go. It turns out to be 4 times by, now my square brackets have approached, up on top of page 101, the primitive of a sine, okay, it tells me it's going to be minus the cos of 4x, and it says but multiply, not multiply, but put a 1 on 4 in that place. Okay, and this was going between a 0 and a pi on 4. Now, even though I might be concerned, all right, because I'm thinking, oh, there's a negative there, have I done anything wrong? Well, right now I'd pause and I'd say, just check, does your sine go to a minus cos? It does. So don't be too concerned. I'm about to just put that minus because the 4 out the front and the quarter go together. So I've got this waiting to be used. So are we okay with that? We've got that waiting to be used. Here we go. Again, I would go cautiously. It's minus the cos of 4 times a pi on 4, minus, and then again another minus the cos of 4 times a 0. Now, minus because when you do integration and you've got a definite, you've got to have a minus in the middle. This is the one where we say, you know, f of a minus f of b, that sort of work. Now, I've written that down, but I'm actually going to, again, take a slight sort of shortcut where I'll say this is just pi, and this says plus the cos of 0. Now, this is where it hurts if you think that a 0 always disappears. Now that you're in trigonometry and exponentials and logs are coming your way today, so this is where you can't disregard it. When it was like the early work, all right, you put a 0 in, it usually just goes away. But this is a cos of 0. So on my calculator, I'm about to do minus the cos, and I know my pi is a 180, and then it says plus the cos, and it says 0. What kind of answer do you get? 2. So it's not 0, but the answer comes out as 2. Now, I just want to point out a few time savers. I don't need to see, neither does Dave, he doesn't need to see all the answers. So he doesn't need to see the last bit plus. He and I both want to see this, and then we want you to use your calculator efficiently. But you don't need to see that minus the cos of pi is 1, plus the cos of 0, which is 1. We don't need to see the 1 plus the 1. You've shown us a great substitution, and then you've been efficient and said, I've gone to the calculator. Now this is area, so it's in units squared. Okay, it's in units squared. Now, at this point, again, Dave was doing a bit of padding, so I'll just pause and say, what you've got on page 100 and 101, quite a lot of calculus. And this calculus is going to come back even in the B3 lecture. So you need to make sure you've got on your resource sheet, you know that the derivatives are going this way, you know the integrations go that way. There's something special about the integration though. It can only work with linears. So say to yourself, it can only work with an ax plus b sitting in that. But a derivative can be as complicated as we're allowed to get in our course, righto? We can ask you areas, we can ask you volumes and all that. Now, at that point, we had a bit of a pause because that used to be the end of one lecture. And then what we used to do is all of our exponentials together. But we've already done a bit of exponentials. We just haven't done the calculus of it. So what you're about to see, right, is things that Dave wants you to use for trivia quizzes. Do you know Dave is a great trivia man? Have you figured that out in your time knowing him? Justin, do you know that? Come up with a question that he won't know the answer to. Please give him a challenge, all right? So, here are 22 things you didn't know or knew, or maybe don't care about, all right, this mathematician. Now, he's got 2 pages there, 102 and 103, and also 104. Make sure you just put on there. It's just general interest, you know. It's not examined. It's all just things that he wanted to fill the lecture with, all right? So, he's got all of these wonderful things, all right? And again, you can play it again on the lecture if you want. So, some people say Euler, but it looks like it's Euler by the looks of that. It talks about, you know, what he was and what he did. It starts with E. He contributed to many things. So he was a great mathematician, so I don't mean to pass by him. He is important, but we don't have a lot of time because we've got to get ourselves through this lecture as well as knowing that we've got to get ourselves in shape for a mid-semester. But the idea is he came up with this number. And what was special about this number, that's the thing at the very end there, is that it's got this 2.7, which is what most people think of it as. They don't remember the rest of it. It's in the calculator anyway. Grab your calculator, find out how you can get the value to pop up. You need to know what e to the power of 1 is. So these calculators, there is some that you can go with the e button, and you need to put the 1 in. So it's an e to the power of 1. And that number there comes up to about the 2.8, okay? My calculator shows it to about there. There is an E, you know where you've got pi sitting as well, down on the bottom button, one of the bottom buttons? There's an E down there as well, if you wanted to know that. Now, what was so special about this, okay, what was so special about it was that it goes on to say that this function is very special to us because it's the only one that its derivative, all right, is the same as the function itself. And that's what it comes down to. So, have a look at the top of page 105. I'm just going to flip through these. This is also the proof on 104. It's just investigating from first principles exactly what was so special about it. And that's what he came up with. Now, there's the answer to a lot more decimal places. All right, so it's like pi, it just keeps going, and there is no pattern to it. And then it says there. So see that bit there? That's the top of page 105. And all that stuff we just zoomed through, what was so special about this number was it says that the derivative of an e to the x is exactly the same as an e to the x. Its derivative is exactly the same as the function itself. Now we're going to pause because that's where we're going to have our break, all right? And then we can take the second half from there. So we've got through all that. I've got some things up here to give back to my group. because I thought you would. Here's an old-fashioned derivative. So now someone throws an old-fashioned one at you and you say, oh, I have forgotten what to do. The 2 drops down, x, and the power drops by 1. Now I'm going to tidy this up. This is minus e to the minus x plus 2x. And if I really needed, because sometimes when I substitute, it's even better to be written as minus 1 with the e to the x on the bottom plus a 2x. Now that's handier when I've got to do the substitution. So as long as you still remember your index laws, that's all that is. And also your plane derivatives. Don't forget your plane derivatives. Righto, are we ready? This guy, it's got an e to the x cubed. So first thing is, if that's my original, then y dash will be exactly the same. So I always write it first. I don't make it go up, I don't make it go down. And in front of it will be the derivative of what you see up there, the function. So if you've highlighted x cubed, the derivative should be 3x squared, sitting in that position. And again, the one under it, or the one next to it for you, think about, all right, where that is. Now that is not, okay, when we were doing round 1 of the derivatives, we had an x on a 3, and I said that's just a third of x. This is something different. So would anyone like to suggest how the 2 over x as its own function should be rewritten? So 2 times 1 over x, which is going to give you, because I need it in index form, so I need 2 times 1 over x, which is perfect, which is an x to the minus 1. Now why have I written that? Because this was the original, so I have no problem with finding that the derivative stays exactly the same. That part's not my problem. It's when I say, now put the derivative of the function. Now if you haven't set it up or you haven't written it on your page and changed it, the derivative is harder, and I know people will make a mistake. But having written it like this, you can see what the function is. So the derivative of this will be minus 2x to the minus 2. Remember? The minus 1 drops, x to the, and then the minus 1 drops by a 1 as well. So that's some old-fashioned derivative. So we're throwing it all in there. You're going to have to say, maybe I'll drive a little slower, I won't be too fast. Now remember, you don't get quizzed on this, and you don't get the tutorial on this until after the break. So we're going to have to relive it again, all right, when we come back after the break. So put as much support as you can down here. Now if I had to write this again, this is correct. There's nothing wrong with that. But if I was doing a substitution, I would probably put that, and then I'd also have this guy sitting in that position. So I tend to find this easier to substitute into. Righto. Now anyone who's ready, there are 2 rules about to come our way. So you can see the questions. I'll just wait for everybody's eyes to stop, and I know that I can go to the next one. All right, have a look, start thinking. Have we seen that rule before? Do we know the rule we're going to use? Are you prepared with all the right tools? What do you think you need for this one? Product. So again, how do you memorize it, or how will you be putting it on? And I remember I've seen plenty of people write the wrong rule even on their resource sheet. So I tend to start with VU dash plus UV dash. You have your own way. You'll write it on yours. Again, because these have got so many components, I'm happy to slow down and to actually set it all up. Like while I'm in the kitchen, get all of it prepped before I put it in, because I just know that there's so many new things. Some people have never done this before. Okay? Now I've paused at the E function. So I've got my U and my U dash. I've got my V prepped. I haven't got my V dash. So V dash should be exactly the same. However, you multiply by the derivative of your function, which is a 4. Now I've got all of it prepared, and that's usually what I look at in your quizzes, and I say, well, if this was the original, then y dash will equal, I've got my rule up high, so I'll go e to the 4x multiplied by u dash, which is 2x, plus, says u, which is x squared, times by v dash, which is 4e to the 4x. I'm very, very cautious. I go a lot slower. Now, you might say, will we get asked to do any more factorising? There are some common factors. I'm not going to stress you out. What I'll do is I will say, I'll put the, sorry, it's my hand that keeps making it do that. So it's got a 2x e to the 4x. It's got a plus x squared, a 4x squared e to the 4x. Now that would be correct. So again, you might say, is that okay? It is okay. The question doesn't say I have to do any more. But again, I'll state to you, anybody that's going to undergraduate maths in some manner needs to know how to factorise that. So when we used to do the product rule and the quotient rule, you would hear us say fully factorised. So I'm going to say, if you needed to do some factorising, can anyone tell me what's the highest common factor you could possibly see? I see a 2, I see an x, and I see an e to the 4x. There's two things left over. From the first bracket, I think there's a 1. From the first term, there's a 1, not the first bracket. And then there's a 2 and an x. Now that's fully factorised, and you've got to remember why you want things factorised, because if they said this was a curve, if they said here is the curve I'm talking about, go find its stationary points always need y dash to equal 0. There's your y dash, and having it factorised means you can put it equal to 0 and potentially come up with some answers. So that's why we did the factorising for that, okay? What's the rule? We haven't tried this one today, so how are the brains going? What kind of rule? Quotient. Can we remember it? I'll quote mine. Yeah, I quote mine like I start with my v's, and then I go v u dash minus u v dash. Now, it makes it really crucial that there's a minus and you've got the right guys at the front. So it's not just anybody can be there. It's got to be the v times the u dash minus the u times the v dash over the v squared. Again, I'm going to prep it because it's got so many components. So here I go prepping. The u is always the top. I've always found some people want to say, oh, it doesn't really matter. It does actually matter. The u is defined as the top function. The v is defined as the bottom function. So you can see all my prepping. It's actually a bit easier. We don't tend to put too much in there because the rule is hard enough as it is. So here I go. Y dash will equal my bracket. I tend to start with my bottom because I say to myself, I've put my v and I've squared it, and I'm never going to touch it again because it does not need to be touched. It does not need to be expanded. So I won't be touching that again. Then I go v, so it's an x minus 1 times by a u dash, and then it says minus u multiplied by v dash. Now the only thing I will tidy up is the numerator, if there's anything that can go. So I'm expanding x e to the x minus e to the x minus another e to the x. So look, there's a couple of things you could do. All right, you could call it x e to the x minus 2e to the x. You could also have taken the, so this is correct, and you could also have gone and factorised the top. E to the x, there's an x minus a 2. Now, why would you do that? Again, because if someone asks you to find the stationary points of this function or come up with some conclusion about them, you need your y dash to equal 0. So you need to know how to solve equations, and factored expressions like this is how you end up solving things. So the other part of this, we've done the derivatives of e's. We're going to turn the page because now we're going to do the reverse of it. So I'm just going to call up what's on top of your page 106. It just says, all right, we know the basic comes back to the basic. So that there is a great question, but there's not going to be that many easy questions. And then it says, now this is what I want you to highlight, and I want you to put some sort of message to yourself, because when you come back to this way after the break, you will have forgotten most of this. So I want you to highlight that guy there. How would you describe ax plus b again? We did it before. Linear. You can only deal with an integral of e as long as what is up there is linear. Okay? So you can't do an x squared up there. You can't do an x cubed up there. You could, as you just saw, you could do a derivative. That's what you were just doing, okay, on page 105. You can put other functions up there, but when it comes to integrating, you can only deal with a linear. So again, we've got to keep our eyes out for this a value. So I'm going to be asking you for the a value. There's 4 examples, and I'm actually going to write my a value every time that I do it, okay? Now this guy here is us. If you did extension, maths at school, you used to be able to do, again, harder questions, but we just don't do those, okay? So don't panic about that. He just wanted you, I didn't know what he was talking about. Well, I knew what he was talking about, but when I read it, I went, what is he on? But he loves finding all these comics and things, all right? So he says, one of the things about integrating, that's Dave's joke, by the way, so don't blame me, right? One of the things we do get a bit upset about is when you're doing your areas and your volumes, you really should know what you're differentiating with respect to. So most people say, oh, that dx and that dy doesn't really matter, does it? It actually does. So if you're going to go into an undergraduate maths, those dx's and dy's really make a difference. So, now that we've got past that, tell me about the a value. So circle it. What's the a value there? Circle it. Tell me what the a value is. Because if you can do that, you're going to have the formula on your sheet. It says it's going to be, oops, wait a minute, we'll start that again. So the first one on your page 106 says it stays exactly as it is. So that's the first thing I do. And then some people put the 1 on. You can do that, or sometimes you just put it over the whole thing. So I'll just say it's a 1 on 2 because my a value was a 2, and I'll put a plus c. Some people just like to write e to the 2x over 2. That's the same, just in case you're not fraction lovers. They are exactly the same thing you are staring at. So both of those are wonderful. So this time around, what's the a value on the second one? A value on the second one is a half. Now that's going to hurt some people because it says e, and this guy stays exactly the same. There's meant to be a 1 over, and then I'll put the half. And it's that 1 divided by a half, which stuffs some people up. The answer comes out to be 2e. This guy's exactly the same, plus a c. All right? So, have a look. You guys can start looking. As long as it's linear, you have the green light. So the next one comes up. Are we okay? Is it linear up there? What's the a value? So can we do it? We can. So it says minus 3 will stay exactly where it is, and then it says there's an e to the 4 plus 2x, and then there's a 1 on, and the a value was a 2. So I piece it together. I will probably tidy it up. Minus 3 on 2, e to the 4 plus 2x. Just in case you want, please don't come bombarding that with absolute values, because a bit of a lesson for your mid-semester, an integral is allowed to be negative. An area is not negative. So someone can say, find me the integral of this, and you can say, oh, my answer is minus 10.5. That's legitimate. But if they had said the area under the curve, then you would have put the absolute values into it. So don't forget, you can have an integral that is a negative answer. How about this, guys? There's a bit of old-fashioned thrown in, and people are going to get thrown by the old-fashioned. So I'm going to put, there's my a coming from there. Now this is actually a little reminder as well about definites, because it's got from 0 to 3. So I don't need the plus c. So here we go, square bracket. It's an e to the 2x, and it's a 1 on 2. That's the first guy. What about the old-fashioned minus 5? What does he go back to as his primitive? Minus 5x. That's an old-fashioned one from 0 to 3. Now again, I slow down when I do my substitution because it says e to the 2 times 3 over 2, or a half of, if you want to write it like that, minus 5 times 3. Now that's me just putting the 3 in. So now I put minus and I start some brackets, because now I'm going back to put the 0 in. And don't just say, oh, the 0 is never going to give me anything, because that's where it hurts. E 2 times 0 on 2 minus 5 times 0. Now what we tend to do is ask you for exact answers. And exact answers mean keep things with pies, keep things with surds, and keep things with e's. So I'm going to tidy this up. It's an e to the 6 on 2 minus 15 minus. What's the e to the 0 give me? 1, so that's a minus a half, and 5 zeros are 0, so they're gone. So probably what I have is an e to the 6 on 2. Now you could give this a few ways, minus 15 and a half if you want, so you could go minus 15 and a half. You could have put it all over 2 if you want, but the main thing is an exact answer keeps the e. All right? Now if I'd asked you, I am going to ask you to do it on the calculator because I still don't know if everybody has found their e button. So just in case you haven't found it, I'll also get the value. This is an approximation. So approximation, I just want to make sure you can all find that guy there. So it's an e to the 6 over 2, and it's minus 15 and a half. Anyone get an answer from their calculator? Just waiting. Kyle took your calculator away from you. It's hard to do in the head. Anybody? 186? Anybody pushing? Justin, James, Jacob? I'm going to go with Justin, and that will tell me if I'm not going well. 186, and it's got 0.21 ... So I just want to make sure everyone can actually do that, because if it does ask you to round off, you should know where it is. Otherwise, you always leave it as an exact. If you don't see any approximation being handed to you, then leave it alone as an exact. Are we ready for the third part of this? So I'll say to you, first part was the trig. What we did was we did derivatives and integration. Second part of this one was e's. We did derivatives and then we did integration. And the very last one that I throw at you is the logarithms. So here we go with logarithms. Now these are spares, so if I get time, I would like to do the exact area under this curve, because it is a very good application of your integration. So I'm going to pause on it, because he hasn't got it in the book. He's got a spare, the equation of the tangent. That's a derivative application. So again, it's a good question, but I'm going to keep going on it. So there's 2 spares if I get time to go back on it. So here's the derivatives of the logs. You guys are on page 107. So it goes through, all right, how we can go from log form to exponential form. And then it basically goes through the whole proof. But the one you really want to put a box around is right at, well, it's already got the box, but you want to highlight it. So it says, you mean that if I get given a log, and as long as it's to the base e, so I want you to highlight, you can't actually do derivatives if it's in a base 10, if it's in a base 5, or any other base. It has to be to the base e, okay? So if you've got the log of x to the base e, its derivative comes out as 1 on x. Now I want you to put a little reminder. There is no log in the answer. There is no log in the answer. So what that means is, when someone hands me a log function and I do a derivative, I don't see the word log anymore. Okay, so that's one big hint, because remember, you're not going to see this for a while. But the only time it might pop up is if you're using a product rule or a quotient rule. They're going to probably still be there. But in general, they're going to disappear. Now, that's the first guy. Not much use to us because he's pretty boring because it's only log of x. So then it says, then you can go through the function version. Again, it's all there as the proof. All you're doing is a substitution, and you get to your second box. Now, that's the one you want to use, because that actually gets you through the easy one and all the hard ones. So I'm going to highlight this. If y is equal to the log of, now it's got an f of x there. Now guess what? F of x is allowed to be anything. You know how sometimes they say it can only be linear or things like that? It can actually be anything. In fact, you really could have the log to the base e of like x to the 5. You could have the log to the base e. You could want to put a sine of x in there. Like, the function is not restricted. You're actually going to have lots and lots of things thrown in there. Now what you want to do, this is what I do, I get myself into a habit. The answer to a log, that means when I'm doing a derivative, of a log, I know the answers are always something on something. So to not make my mistake, I do this. The f of x gets thrown straight on the bottom, and then I do that and say, now your derivative should be sitting on top of you. Again, put a little note. There is no log in the answer. You cannot see the word log in the answer. So here we go. We're about to put those questions into practice. So it says, I'm going to set it up over here because I will write the y. The ln, remember, is the natural log, so you're allowed to differentiate it. And it says that y dash will equal, on the side, I always write my f of x, and then I say f dash of x. Now, because you're going to have it in on a piece of paper, you don't have to memorize it. Have you ever realized that if you memorize things, it takes you less time? Because I know a lot of people say, I ran out of time. I didn't get there because I ran out of time. If you actually memorized a lot of this, you wouldn't have to keep looking it up. That's just a general idea. That's for this mid-semester, as well as for the final, a bit of advice. You know you'll have it anyway. You'll know you're allowed to bring your resource sheet in, but the less you have to flip it over to look at, the better it will be for time. So here's what we've got. Y dash, there's my fraction. Function goes on the bottom, derivative goes on top. And I talk to myself, function on the bottom, derivative on top. Anybody game enough to cancel? Anybody game enough to cancel? No, don't touch it. Cannot be cancelled. That's round one. That is round one. So are we done with? So, round two. Okay, it looks like this. The log of x to the 4. So again, say to yourself, this is the log of a function. Highlight it for yourself. Again on the side, because I have it on a different page, but I'm going to keep writing it. Yours is all on your page in front of you. I write that down because I know. First thing I do is start with the function on the bottom, locked in. Now do its derivative, 4x to the 3. Now can that be simplified? Yeah, it can. What's it come down to? 4 on x. Now I'm going to show you. Anyone remember log laws? Log laws. Where's that 4? Go back to the original function. Go back to the original function. Wait a minute, that pen there. Go back to the original log of x to the 4. Can anyone tell me a log law about that 4? What can that 4 do? Oops. What can that 4 do? Come down. And guess what? If you did the derivative this way, it is exactly the same answer because it's 4 times the log of x. X is the bottom, derivative on the top. You still get a 4 on x. So even if you had applied your log law, you'd still get the same derivative either way. Okay? Now, before I turn, because I have to wait for people's eyes to stop looking up there, have a look at the third one. We're about to be hit with a log of. Now, if you just put your finger over the ln, what are you staring at? Well, I'm staring at a function on a function. And I know that when I get asked the derivative of that guy, what kind of rule will I need? Quotient rule. So this gets a little bit heavier, this one. So are we ready? Here we go. Again, I'm just going to set myself up because I need f of x on the bottom and I need its derivative on top. Now, I've just said that this obviously has a lot more happening because I can do the function on the bottom. There it is there. There's the function on the bottom. But now I'm asking you for its derivative. And I've got to pause because its derivative is going to need a quotient. So here we go. Let's set it up. U is 2x, so U dash is. V is 6 minus 5x, so V dash is. Now I've just taken a pause. I tend to do my, and remember in your final exam you have lots of paper, okay, to work with. Quizzes you're a bit restricted. I'll have to see if we can make it 2 pages. So U dash is 2 and V dash is minus 5. Now I'm just going to do a small quotient rule over here, which is V U dash minus U V dash. Remember, I need all of this because I need the answer on top. I've got to do all this work. So v is 6 minus 5x squared. On the top I've got a v, which is 6 minus 5x multiplied by a u dash, and then it says minus u multiplied by v dash. Here we go. Let's see what we've got. Please do tell me if I make a mistake, because I'm up here looking at lots of things. I get a plus 10x. So it looks like I'm going to get a 12 over a bracket being squared. So I'll wait to hear some sort of confirmation. Are we happy? Can anyone see any errors? All good? 12 minus 10x, and it was nice that the 10x disappeared. Now what was I supposed to do? Put the derivative on top. So I'm about to put that answer on top. So it goes. The guy on top will be 12 over 6 minus 5x squared. Now that's a pretty big hurdle you've just jumped over. However, there's still the tidying up. And what are we all lovers of? Fractions. We love our fractions. Now I can see a fraction divided by a fraction. Do you remember old-fashioned fractions when no one had a calculator in their hand? A fraction divided by a fraction, what do, Rebecca? You flip the second one. So I'm going to write it out. I'll put, this is a 12 on a 6 minus 5x squared divided by a 2x on a 6 minus 5x. Now, Rebecca has said you flip. It's the second one you do the flip to. So it's 6 minus 5x heads up there, and the 2x heads there. Now, we are almost through, but this is, again, the time-consuming part. It shouldn't be time-consuming, but because we're not lovers of fractions, it takes people a lot longer. I'm going to say, as lightly as I can, this fraction goes, this guy here goes with one of those, so this has got a 6. There's a 6 minus a 5x on the bottom. This has got a 12 and a 2, so this goes once and this goes 6. So it looks like it's left me with a 6 and just another x on the outside. Front or at the back of that bracket, doesn't really matter. Anything else to do with it? Can I do any more cancelling? Anything else to chop off and simplify? Now that again takes up a lot of skills. Okay, you can see how much work you had to sort of do. You had the idea, you knew that it was f dash on f of x, even if you try and fill in small parts to it. And you've got to be careful at every single spot. Yeah, Justin? Again, you can say 6 over, you can say 6x minus 5x squared. Is that what you want, Justin? And you can, totally true. Wouldn't be much use to you, because about the only thing you ever do with it is if you put y dash equal to 0, the denominator always gets disintegrated anyway by the 0, if you know what I mean. That's why we don't put a lot of effort into the denominators, because when you think about it, what do we do with the answer? We might put it equal to 0, so that denominator wouldn't matter anyway, yeah. Oh, Justin, wait till I tell Dave. Oh, Dave used to, every time someone did that, he used to put a puppy, you know, dying or a cat dying. He had to stop doing that because all the cat lovers weren't real happy with him. Every time, Justin, someone did an illegal cancel like you just did. So this is what Justin wants me to do, all right? Justin wants me to cross this and this out and get that. What are we going to tell him? Can't do that. You can't do it because you need it to be factorized. That's why you would never do it. That's why this is the best place to leave it. Because if you are going to cancel, I was looking for an x. If I saw an x there, I would have cancelled it. But what you've just done is ignored the fact that everybody there has got a bracket around it. This was actually a 6 over a 6x minus 5x squared. And your job is to say, that says 6 divided by all of that guy. And what you just did was cancel a bit of him. So not doable. I'll have to go like this and put cat dies. Okay? That one's for Dave, because he used to have that dying all the time, because it was one of our biggest hates, is that people do a lot of illegal cancelling. Now that's a pretty big one. We've also got one more there. That's pretty big, all right? And then we can at least take the next last page on. So here we go again. First thing, put a circle around what you think the function is. I think the function is that. Okay? So when I go to do the derivative, it's going to be f of x on the bottom followed by f dash of x. Now I've already started. The thing about, I was reading one of the little extra things I find around the uni, and there's something called Maths Tune-Up, and it was just giving people an idea entering uni if they haven't done maths for a long time. And it says understand the question, and then it says things like, you know, make sure you can see your path. Don't start going crazy driving if you don't know where you're going. I can, just by putting that in front of me, I know where I'm going. I want the f of x on the bottom, and I'm going to need the f dash of what I circled. Now what I circled needs a function of a function rule. So I can already see where I'm sort of heading. I can understand that there's a lot to do. So here's what I'll do again. Ready? This one would have been, it says again, you need the function on the bottom, that's an x plus 4 to the 5, and you need the derivative of that. Okay, it's just a chain rule, old-fashioned, we did it in first semester. Hasn't got any e's in it, hasn't got any trig in it. So it's a drop the 5, x plus 4, then it goes to the 4, and just put times by 1 because you have made me feel better that you did check the derivative of what's inside. Is there any simplifying? Now this one, Justin, because it's all factorised on the top and it's all factored on the bottom, that's why having a factored answer helps you. So it looks like there's 4 of these brackets and 5 of them down the bottom. So when I cancel, I'll get that and I'll get that. So there are 4 of them on the top, there are 5 of them on the bottom. Guess what? You could also have used your log laws, same as before. If you had started with the log of x plus 4 to the 5, log law says that's the same as 5 times the log of x plus 4. Its derivative is 5 times function on the bottom, derivative on top. Guess what? You get the exact same answer, perhaps with a little less work, might be as much work. I don't think it really matters in that one, on both of those. Are we done? Now, this is the last bit. So the last page says, okay, we're almost there because now we do the flip side, which is, can you integrate? Now, you've got to be very careful. This does not say you can integrate the word log. You never can, okay? This clearly says you can integrate a fraction type function. So the giveaway is, every time you see the integral, now remember, you're not going to get this on your mid-semester. So on your mid-semester, you will not see logs anywhere in there. Now, I'm going to put up some questions which might look similar, but I'm going to point them out to you. So bear with me for a second. This is what it says. The basic idea is that this is, again, Dave going off because he was doing a filler, and then he says, but we don't integrate logs. Basically, he hasn't written that in your book. So could you just say, we do not integrate? That means you will never get integrate the log of blah, blah, blah dx. You will never get that, all right? A little bit too much for our course. So it's not what we're going for. What we are going for, though, is that if you get an integral and you see a fraction. Now, I'm going to say, in your test this week, you still might get some that sort of look like this. So I'm going to put them down as I do each of those 3 examples and show you the difference. When you're in your final exam, all right, you're going to get all of it thrown at you. So this is where you want to be careful, okay, as you go along. That's the first rule, and it says x has to be greater than 0. Oh, he loves that guy. Okay. Here's the one you want. See this guy? It's the second one you've got written up there. It's the most important. It says, whenever you get an integral coming your way or a primitive question, all right, an area under a curve, those sort of things, if you see a fraction, then this is what I want you to do. Put the word check. I want you to check that. Start from the bottom. If you see the function that you have at the bottom, so you can stare at the function on the bottom, that's easy. Ask yourself, what's its derivative? And you'll say, okay, I'll ask myself, what's its derivative? If you see the derivative and it is sitting on the top, then the go-ahead All right? All clear. Go for it. Green lights, go. Now, there are some times when we have to pause, though. So I'm going to run through that same. See how I put check? Start at the bottom and then wrap yourself up to the top. Are we ready for these guys? Here we go. First thing I'll ask, all right, is this guy says, I see the fraction. I've got a bit of a suspicion, especially because it's on this page, that it's got logs in it. But here's the question. My thought was, check the bottom. So this is what I'm about to do. I'm about to say, x is on the bottom, true. What's the derivative of x? What's the derivative of x? 1. Have I got that on top? Well, I've got 3 lots of 1. So what I'm allowed to do is I'm allowed to push the 3 out because you've always got to have what you were given. Now, if I did not put that 3 on the outside, it wouldn't be equal to that because it would have said, well, where'd the 3 go? So have I still got a 3 over an x if you put the 2 back together? You do. So you've got the green light that this is now able to be done. So I'll put this is now 3 times the natural log of x with a plus c. Now, you don't need to write the multiplication, but I just thought I'd put it there so you can see the constant multiplied by the answer and then the plus c. Now, I'm going to come back to that PowerPoint in a second and show you something compared to this week's test. Here's round 2. Round 2 question says, all right, I see the fraction, got a bit of a gut feeling, I think it's logs because it's on this page. I want you to start with a check, which is, start down there. If you've got an x cubed minus 4, what's its derivative? 3x squared. Do you have 3x squared? Now this one's been given to you, handed to you, if you want, on a platter. So everything is ready to go. The answer will be the natural log. Now remember, you're allowed to put ln or you can put log to the base c. And what's supposed to sit here is the function, the guy that's on the bottom. The function is the one that's on the bottom that I'm pointing to. Okay? Now, the next one looks really similar to the one you just did. So it's not a misprint. Have a look at the last one that you've got. Looks very, very similar. First feeling, it's got a fraction. I think I'm going to go and check. First of all, my thought is, if this was my function, what's its derivative? And you would say 3x squared. But the original question didn't have a 3. Did not have a 3. Now, it's a constant. So I can counterbalance it, if you want to put it like that. I can even this back out by doing what out the front? Timesing it by a third. Have a look at that third that I brought in. First of all, you can bring in a constant. It's not an x you are bringing in. You're never allowed to bring in a variable, but you can bring in a constant. So what I've done is said, have I still got the original answer, the original question? See the 1/3 times the 3? What's a 1/3 times the 3 give you? Just a 1. And that was what the original had. The original just had 1x squared. So I'm allowed to put this 3 as long as I counterbalance it with that. Or put some words down there that will help you remember, because you won't get to practice it this week. You'll probably see it a little while away. Okay? So here's what we've got. The green light says the third stays there. It's the natural log of the function, and then I put the plus c. Now, before I go any further, I'm going to go back on those, but just the second and third are very similar. I'll just deal with the first one and the third one. So I'm going to go back to the first one and show you how it can be confusing for the test you're about to do this week. So can I go back? Everybody ready? On this one, I want you to say, but what if you got asked the integral and I put the x on top and the 3 on the bottom? Does that need a log? Does that need a log? What kind of function is it? That function's linear again, because it's just a third of x. So can you integrate a third of x? I hope so, because that's the sort of thing you might get in the test on your tutorial. I'll just do it for you, which means the x, the third can stay out the front. Doesn't really matter what you do with it. I'll put it in there for a second. The x goes up and the 2 goes there. So in fact it's x squared on 6 plus c. Now I want you to say to yourself, that could be in your test. There is a difference. All right? So just because you see a fraction like x on 3 with an integral on it doesn't mean it's going to send you to logs. Can you point out to yourselves, because remember you're not going to see this side for a while, the x is in the denominator. Now if you remember, when we started primitives, we said something like this, that you could do any of these except one. There was one that could not be done. Do you remember which one that was? N could not be. Anybody remember? N could not be. N could not be minus 1, because if you got x to the minus 1, that's like asking you to say, in the first time we did integration, you would have said x, you would have added 1, and then you would have divided by the same number. Do you recall that was the one that we could not do, the integral? We could not do it at that point. But now we can. So it lives on its own, and what makes it so special is the x is on the bottom. Now I'm going to go to the third example and show you what might happen in this week's test. In this week's test, I'm going to say, just because, all right, I've got this on top of this on top of that, could you integrate that question? Now that's a different question. And the reason why that could be done and could be in your test this week is because there's only one term on the bottom. So that means you can break this up so it looks like this. And it means that you can say this is an x, this is a 4 to the x to the minus 2. The answer to this will be x squared on 2 with a x to the minus, I've got to add 1. Now, I won't finish that off because it needs a little bit more tidying up there, that last line. But there is a difference. Have a look at that question for week, what are we? Week 8. All right, B2. All right, B2 sort of lecture. But when I changed it around, what makes the difference? Can you say to yourself in words, the first guy, that's on page 108, when you have more than one term in the denominator, an x cubed minus 4 means I can't do the split like I could have on that guy there. Okay? Yeah? If I was cleaning it up, that's a positive, that's a 4, that's the x living on the bottom. That would be its nicest position. Yeah. Now, I'm just going to flip through for a second because just for a moment, we know that we're not going to have this week. However, there are spares, and those spares will go along, and I'm pretty sure he put some area. Oh, he didn't. He just put some extras in. I thought he was going to do some areas under the curve. All right? And he didn't. So guess what? We're at the end. I'm just going to put up that mid-semester again so that you know it is definitely there, under that one there, mid-semester. If anything goes wrong this week and you have a problem, ring or email.